Hello, my physics students. Here is a very interesting question which combines the Doppler effect, beats, and resonance in open pipes. So we have three concepts combined into one question, and let's see how it can be worked out. First of all, let me read the question. On a hot afternoon, you are watching the rehearsal of a marching band. On a level field, you are standing 9.48 meters from a flute player who is also standing still playing a single steady note, which happens to be the second harmonic frequency of the flute. A trumpet the same distance away is trying to play the same note, but his instrument is out of tune and you hear a beat frequency of 3 Hz. But when the trumpeter marches toward you at the speed of 1.4 meters per second, the beats disappear. The speed of sound on this day is 350 meters per second. A. How long is the flute? And B. As the trumpeter walks towards you, he passes certain points where you cannot hear much from either the flute or the trumpet. One such distance is 7.3, that should be 7.38 meters from you. What is the next distance to you? All right, first of all, let me break this down for you. Now, the flute player and the trumpeter are at the same distance initially, and the problem says that the trumpet is out of tune, and the frequencies of the trumpet and the flute are different, and the difference is 3 Hz. Because the number of beats in a second, or the beat frequency, is the difference in frequencies between the two. So when the question says that the beat frequency is 3 Hz, which means there are 3 beats in a second, that must be the difference in frequencies of the trumpet and the flute. Now, the second point is, when the trumpeter marches towards the listener at the speed of 1.4 meters per second, there are no beats. Which means, as the trumpeter walks towards the listener, the apparent frequency of the trumpet goes up by 3 Hz. And this is called Doppler effect. In Doppler effect, the frequency of a source appears to have changed because of the motion of the source or the listener. In this case, the listener is at rest, but the source, which is the trumpet, is moving toward and therefore the frequency appears to have gone up by exactly 3 Hz. So here's how we work out the problem. First of all, we have the formula for Doppler effect. And in this formula, F prime is the apparent frequency, F is the actual frequency, V is the velocity of sound, VL is the velocity of the listener, and Vs is the velocity of the source. And I've already explained that F prime is the apparent frequency, which would be the actual frequency plus 3. So combining beats and Doppler effect, we get this. Remember that the listener is at rest, and that's why the velocity of the listener is 0. So when we do these calculations, the right hand side, when you do this, becomes 1.004016. And then when you do the algebra, you get the frequency to be 747 Hz. Now that is the frequency of the trumpet. which means the frequency of the flute must be 747 plus 3, 750 hertz. I hope that's very clear. Now, when we go to vibration of air columns in pipes, the formula for the frequency is given by N times V by 2L, where N is the number of the harmonic, in this case N is 2, V is the velocity of sound, and L is the length of the pipe. Now that's for an open pipe. A flute is an open pipe. So substituting that, and since we know that the frequency is 750, when we substitute that into this formula, you have 750 is 2 times 350 by 2 times the length. The 2 and the 2 cancel out, and then you calculate the length to be 0.47 meter. All right, so now we go to the second part. The question says that as the trumpeter walks towards the listener, there are certain points where you cannot hear either the flute or the trumpet, and that is because of destructive interference. And that means the waves from the flute and the trumpet cancel out. And that happens when the crest from one is superimposed on the trough from the other. So the maximum positive, which is the crest, falls exactly on the maximum negative of the other one, cancelling it out. Now for this to happen, for destructive interference to happen, there is a condition. The condition is that the difference in path, which in this case is 2.1 meter, should be given by m plus 1 lambda by 2. So that's the condition for destructive interference, where m can be any integer starting with 0. So since we know that the path difference is 2.1, we set the condition for destructive interference equal to 2.1, and we are going to calculate the value of m. But we do not have the wavelength, which can be easily found out, because wavelength is speed of sound by frequency. Speed of sound is 350, frequency is 750, and when you divide them, you get 0.47 meter, which is exactly the length of the open pipe, which is true because it's the second harmonic. So when you put that back into this formula, we try to calculate the value of m. Well, I used a more accurate value, 0.4667 for lambda, and then rearrange that and try to get the value of m. Get m plus 1 is 9, so m is 8. All right, so now the question is, what is the next distance closer to you that this is going to happen, right? It's already happening. So what's the next distance? Now we know that m is equal to 8 in this case, so the next destructive interference will happen when m is equal to 9. So we're going to once again use the same formula, which is the condition for destructive interference, and put the value of m as 9. So 9 plus 1 gives 10, and you have lambda. by 2. When we do that, we get 2.33 meter, which means the next distance must be 9.48 minus 2.33, which is 7.15 meter. So when the trumpeter is 7.15 meter away, again the sounds will cancel out. So I hope you understood this good question where we use Doppler effect, beats, and resonance in open pipes. Thank you and good luck.